Hello, welcome back to the video series for Geography 300, Geographical Data Analysis at WVU. This really will probably be the last really main video for this course. And part of it is to summarize a lot of what we have seen, especially in sort of the middle part of the course. And it's to set you up for what is the final lab for the course. The main focus here is picking a topic. Now, or picking a method. You will not usually be told in a regular situation, out in the real world or what have you, you will not be told you need to use this technique. You need to follow the steps in this set of instructions. It will just be, okay, find out something about such and such topic. Please tell me, why are there excess disease cases in this county? Analyze that. Analyze the traffic patterns so that we can decide where to put new bus stops. Tell me about the income distribution of a place so that we can decide where to put things like, say, food pantries to help the less well off. You'll want to be able to take those kinds of requests and take them and figure out, okay, how am I going to analyze that? What data do I need, and what methods do I need? So that's what this is about, and it's going to be a longer video too, because this isn't something that can really be broken down into smaller chunks. So I'll start by going back and, in a way, revisiting even the first thing on the course. The first subject for the videos where we had that process of, you have the general problem, you collect data, you run the descriptive statistics, you generate a hypothesis that can fit into the inferential framework, you run an inferential statistics test to evaluate that hypothesis. And item number 6, at the end, you take those results and you apply them to some kind of policy or decision making. We've spent a lot of time in running an inferential test part, step 5. Now we're going to step back out and look at that broader context. So I will take an example of, say we had a major severe weather event, a derecho perhaps, one of them that's kind of more likely to occur here, that's happened since I moved to Morgantown. So we have a derecho, massive windstorm, I've seen it described as a straight line, as a tornado that is in a straight line. So very high winds, it causes quite a bit of damage. And so you're getting initial reports, and you are, say, in charge of whether it's through the state coordinating with FEMA, let's just say working with FEMA to pick something here. And FEMA wants to know, where do they need to set up the tents and their relief supplies? Okay, that's a broad topic. And I'll start with that broad topic here. So we need to decide where they're going to go. Okay, the next step would be, what kind of data do you need? What kind of data will help answer this? Okay, so we might look at disaster, like people calling in on to say, here are the needs. So we might have wind damage reports. Power outage reports, and the data from the weather stations. You can probably think of other data that we might want to help make this kind of decision. We'll go with this, and we'll illustrate and point out one of the things could be data limitations. What is or isn't available, especially in something like this that will be a pretty fast moving situation. In, say, some of the later hypotheses, we might look at, excuse me, we might look at that effect. But we'll start with here these sets of data. Okay, we can then, as the next step there, running descriptive statistics. A simple thing would be to just put them on a map. Where are the wind damage reports? Maybe do a maybe do a standard ellipse of the wind damage, of power outage. We could find the average number of people affected for each of the power outages, or the average number of people in each county affected by power outages. And that illustrates something else where what we're doing here is, in a way, transforming the data. These reports might be coming in with a person or with a small polygon. And it might tell us how many people are estimated to be affected. We're then combining those, merging those by county, aggregating them to get this additional piece of information, this additional set of data. This may help with some of the later on decision making. So we have these, I'll work with these as the descriptive statistics for now. Again, you could possibly think of more that you may want to do. And also, there can be a cycle back and forth. It's not a straight shot. Number one is identify a topic. Number two, collect data. Number three, descriptive statistics. Number four, formulate a hypothesis. That's the nice cut and dry, straightforward approach, but it often doesn't work that neatly. So we have this for now. The next thing can be formulating that hypothesis. So now our hypothesis, okay, if we want to identify where we want to put the FEMA relief efforts. This is something where we can probably go many different directions. I can say the first approach I would take, and that's what I'll illustrate here, would be, so if I put myself in the position of somebody deciding where should those go, I want to make sure my supplies go to the areas of greatest need. How could I find areas of greatest need? Well, working with this county data, and this can also be the amount of damage per county. And we could have this as average, or we can also work with the totals. For finding the areas of greatest need, we may actually want the totals instead of just the average. Where if we have 100 people calling in with small amounts of damage, do we want that, or would we want one person calling in with a large amount of damage? We might be mainly interested in the total. As in many cases, arguments could be made otherwise. You could argue that you want the average because, okay, if one person is calling in with a huge amount of damage, chances are other people nearby may also have a lot of damage, but may not be able to call in. So you could argue the total or the average. That's something that you can make your choice and justify. That is going to be one of the key lessons here. In many cases, you can have multiple different techniques that will help you with this broad situation. But you'd want to be able to explain and justify that choice. Why did you make the choice you made? So here, that said, find areas of greatest need. Okay, finding areas where there's a lot of need, this may suggest I want to find places with a lot of damage that are a lot nearby other places with a lot of damage. Okay, now we're starting to perhaps get somewhere in identifying that technique. That this should sound familiar, where I want to know where there are areas with high damage that also have neighbors with high damage. That's going to be the areas of greatest need. Okay, so That suggests local Moran spy. Also called MESA, local indicators of spatial autocorrelation. So now we have our technique. In many ways, once we get to here, it's easier. That I now have my technique chosen. I have my data. I have it set up per county. Now I go, I put that into Lisa. This is a situation where perhaps clean contiguity would make sense. I really want to have ensure good neighbor relations. Nearby, really being nearby, because especially in this kind of environment, people may not be able to travel really far. So, we run Lisa. I gave a reason for queen. I run that, and I get the maps at the end. I can then go and write my report and say, you want to put your relief efforts in those areas that in this map, in the output cluster map, are going to be bright red. At least if you're using Geoda. They're going to be bright red as the default color for high clusters. And you can then circle this back and in your decision say, I want high, I want the red areas as the places where there should be relief centers. This is a very simple, straightforward example. I can then highlight now something really from just the past week that I was doing, which I'll take you through how I used a large part of this process for the talk I presented at the conference I was just at, virtually, the American Association of Geographers. So for another example of stepping through this process, there's an overarching goal for the project I'm working with. And I'm working with about 7 or 8 other people from WVU across the Everly College of Arts and Sciences. So I'm there with geography. There's also people from political science, communications studies, from psychology, and maybe 1 or 2 other departments. We're all working and studying how how people responded to and reacted to and understood really the COVID-19 pandemic as it entered Appalachia. So That's our broad topic. Now, within this broad topic, we actually have different people taking off different parts of that. The part that I was looking at, and really that I wanted to look at, and this will show up really when I get to step 4 here. Part that I wanted to look at is the extent to which the, at least perceived, if not the actual, or kind of both, accessibility of healthcare facilities and COVID testing facilities. How did that shape people's willingness to take action and to get tested? So things like, if there was poor equity in access to testing sites, how did that affect people's willingness to get a test? So in terms of the data, so we have the data as first, and this was, we submitted a grant through the National Science Foundation and got it to collect surveys of people living in Appalachia, 4 subsequent surveys, the same people, from in 2-week intervals from early April basically through mid to late May of 2020. Okay, so we have this data and we asked literally hundreds of questions. And we had, say, almost 5,000 people answer at the first wave in April. Not surprisingly, the response rate for the survey dropped from stage to stage. And we still had over between 700 and 800 answer in the last stage, which was apparently, this is the first time I've been involved in a project like this. For the people who were, they said that was what they expected. So that even though that was a lot of drop off, they were kind of prepared for that. Okay, so as I said, we have the data, and the first thing I did really was to pull out what from these hundreds of variables was of greatest interest. So the demographics, how old was the respondent, the gender of the respondent, the race of the respondent. We would expect all of those to play a factor in the extent to which they're willing to get help tested or to access healthcare. We got the approval ratings, how much they approve of how well President Trump handled the pandemic and was handling, and how well their governor was handling the pandemic. Another thing that I pulled out was we'd asked about their attendance at church services. Useful both in the sense of that may impact their willingness to seek medical care, depending upon the church, that is. But also knowing that in the early time period for the pandemic, many times people caught COVID by going to church services. There's a place where a lot of people gathered in one room, in the sanctuary, in close quarters, and it became what later we'll get the term super spreader event. And so that could also represent an increased risk of getting COVID, as well as something that could affect how people respond, or would think of responding, what to do if they got it. And several variables under what I put here under the heading of barriers to access, barriers to getting tested. Things like, okay, how many minutes would it take them to get to what they think is the nearest testing site? How many minutes would it take them to get to their primary healthcare provider? Do they have a car? If you don't have a car, it's going to be a lot harder to get there. Do you have health insurance? If you don't have health insurance to pay for any COVID treatment, you might actually just not bother to get tested. And you certainly would be more hesitant to getting care unless it were really, really emergency. So have those kinds of barriers in here. And how likely are they to seek care, whether through their primary care physician or by going to a hospital? How likely are they to get tested if they experience symptoms? This, and I've looked at several of these through descriptive statistics. I'll highlight here one. I did how likely to seek care and testing. It was on a Likert scale. That means not likely at all to 7 being very likely. The next, and what I did was, I did a histogram of these 7 values and found most were 7. Very likely. So then what I did was to turn to a binary variable where a 0 or 1 value very likely became 1, everything else was 0. Now I have here the data. I can then go to different, then what would I do for the regular, for the step 4? Identifying my hypothesis. I will illustrate there are several ways I could have gone. So part of this is thinking through how to work with the data that you have. So the first thing could be I could divide the people into two groups. For are they likely to get tested? Very likely, or not like, or anything else. Okay, so if I'm thinking through, so very likely to get tested versus anything less than very likely. That ranging from likely to not at all likely. So you might think, what techniques were designed to work with this kind of data? Okay, we've seen something like that in this class. And this is where it can be really important to engage what I would call analogical thinking, like analogies. I have seen something similar to this. I recognize that situation, and what I did before in that similar situation can translate to here. So you might see, very likely to get tested, two groups. Okay, well, I've seen something with two groups. Like, there was a lab in which we're comparing, say, the likelihood of, or dividing the state up by congressional district. Ojada's district, number 3, versus the others, numbers 1 and 2. Okay, what did I do when I had things split in half? That was a t-test. So I could go and say, so I could take that travel time variable and have a hypothesis. Those who are very likely to get tested, who say they might live closer to testing facilities. Okay, so now what do I have? I have, this could be a t-test. 2 sample, and I'm saying shorter. That means one tail. I'm specifying a direction. So now I can put the data in, and run that and get a response. That's one option. The thing is, we have many things working in concert together. And this is only going to look at one. And I could put in the age instead of the travel time. I could put in education levels, income levels. I had those data too. I could put in all sorts of things to this. But what I want to do is look at everything together. And what that ends up doing actually is a technique that is not directly one that we looked at in this course, but it's very similar. So for the purposes of this course, that's probably something you could do. So okay, again with thinking and with analogies. Really what I want to do is to use all the variables that I had prepared to predict whether or not a person is likely to seek testing. Okay, what have we seen that will work with all variables at once? Okay, well, you may have, this could be very familiar very recently, because trying to use a whole series of variables to make a prediction about one, well, that sounds a lot like multivariate regression. And that indeed is what I used. The only difference was where, and you may have noticed this in the GWR, where, okay, you had to make one of the choices of Gaussian kernel or a logistic kernel or a, I think the third one they put in was something like binomial, but I could be wrong. I just told you to pick Gaussian and not worry about it. When the outcome is a 1 or a 0, a binary outcome, that actually would mean switching over to logistic. Changing a setting of that variable or that parameter to match the variable. That's the only thing that is different from what you have seen in this course. So I did this multivariate regression. I also recognize that Appalachia, even if people from outside the region may think so, it's very much not homogeneous. Especially if you're familiar with the Appalachian Regional Commission and the boundaries for that, it actually stretches from western New York all the way down to the northeastern corner of Mississippi. There's enough variation there that I was not going to assume that the relationships between the variables here are going to be consistent across space. So I also did a geographically weighted regression. And for that, I used the number of the nearest neighbors. This gets to another factor here of what does and doesn't affect our choices. The data that went into this are individual people. And depending on when you actually watch this video, you either will see or have seen in class, probably have seen, the issue of geospatial data and privacy. So this individual level data, the only spatial data that we collected was their county of residence. We did not ask anything more detailed than that, basically because you start to get into real privacy implications in doing so. Especially when asking questions like, have you gotten tested? Have you been diagnosed with COVID? There are many more restrictions on the use and access of data like that if you, even anonymous, even without the names, if you go at a smaller spatial scale than the county. So we did the county, but I had the individual records even so. So I had a series of, so I had all of the surveys spatially recorded as points so that they could be separate records as accessed by ArcGIS. all of them located at the centroid of their respective county. So if there are points, that rules out contiguity. I can't use contiguity on points because they don't have neighbors. Then it's either a distance threshold or the number of neighbors. I picked the number of neighbors because the number of responses per county is highly variable. Because the population is highly variable, that wasn't a surprise. There's more responses from Allegheny County, Pennsylvania than any other because it has the highest population. It contains Pittsburgh. And some of the more kind of rural areas, most counties in West Virginia only had a few, if they had any. So, because of that, if I was to have a radius large enough for the GWR to work with that idea of local multicollinearity, a large enough radius to work in the very rural areas would be so large that working in Pittsburgh would not show as much that's useful. So I did nearest neighbor. And what I did was basically go a little bit above what was needed to avoid multicollinearity errors, which was 500 for the first two waves, 400 and 250 for the third and fourth wave respectively. So okay, I had this. I have the GWR. And in many ways I am in the process of writing things up. Yes, I presented the results, I have the images, but I haven't formally written anything yet on it. And this is where I get to that lesson of, as much as things may seem nice, neat, and straightforward, I've even presented here the idea of, here's what I did. I did this, then this, then this, and so on. It's not that neat and tidy because GWR results. One thing I found was that during our time period, in that, it's been erased, in the April to May time period, towards the end of April, in Georgia, Governor Kemp announced he was opening up the state. He was lifting the restrictions, pretty much the first state to do so. That changed things dramatically, and in the GWR, the effect of the approval rating of the governor upon whether or not you are likely to get tested completely stood out. Like, even though I didn't code the county or state lines into this analysis, you can pick out Georgia. It's that clear. In pulling out a region where people who disapproved of the governor were then far more likely to get tested than the people who approved of the governor. Okay. But, and this is where it gets to that, I recognize the way I had phrased this kind of implies what could possibly change is people will still approve of the governor, but they might change their opinion on testing. When I think it's really the other way around. That people's opinion of testing stayed the same, but they disliked what their governor had just announced. And it shows up in the second set of surveys clear as day. I would then want to go back, maybe even collect more data, pull more data out from the survey. Because there's data about anger towards politicians in there and things like that. And I might then say, what affects your approval rating of your governor? I might also go and pull out some of the qualitative answers, like the written answers, to see if people wrote out and expressed what they felt about that decision. So having found the results here that were not necessarily what I would have initially expected. I then go back to previous steps. I revisit what I did. I do more analysis, I do more work, so that I can then get a clearer picture of this broader topic. And so we see things going back and forth. And it's not that neat and tidy. So there's two examples, taking us through that process. Now I will go and really highlight some of kind of the decision-making process for that step of what test or technique do I want to use. Much of this is things I have said already. I'll just put it in here, and as well in a context of reviewing many of the techniques we've seen. So, first thing could be, we're going to pick a test. What kind of question am I asking? One broad category can be, are the means of a group equal to each other? Okay, we've seen what to do here. And it's in part a matter of how many groups are there. If there's two groups, we would want t-test. Also, we had the before and after as the paired t-test. Likewise, if we have three or more groups, that becomes ANOVA. We saw chi-squared as a means of assessing predictions. So if you are trying to, as it says, to say, here's what I think could be the case, could be a value, was it accurate? That's where chi-squared comes in. That especially shows up with are points clustered or even or random? We had different techniques for point pattern analysis with this kind of question. And it's important to note, often, not always, but often, if you have point data, you might be wanting to do this, but only if what is interested are the locations of those points. Point pattern analysis does not deal with the attributes, it only deals with the locations. So if your goal, if your task is not about the locations, but about the values, you might want something else. But if you want to know, are the points clustered? That leads to point pattern analysis. That could have been used, as I said, there are many things we can do within our broad techniques or our broad topics. With that first topic from the start of this video, the FEMA one, we could use a point pattern analysis to say, are the locations of damage reports clustered? Are the locations of power outages, if they're recorded by an address of someone who calls in, are those clustered? And if they are, you then want to map it out, find the clusters, and go there. That could be another approach than what I illustrated of local Moran's eye. So again, to highlight, there are many cases where different approaches can be used for the same problem. And it becomes a lesson or an issue of, can you justify that choice? So then that gets to, I want to put it in this framework. Are the group means equal to each other? Am I assessing predictions? Am I asking whether or not points are clustered or even or random? We can say our values. If the attributes are clustered, we can say, okay, I want to look at Moran's eye and or Lisa. And everything we've seen in the last 3 labs has been within the framework of, I want to use one or more variables to predict another dependent variable. And we saw previously the idea of then picking a spatial regression. And you first, in many cases, using Moran's eye of the residuals to assess, is there autocorrelation in the errors in this linear regression? Then we can pick, okay, why do we think there are errors? Why would there be spatial patterning to the errors? Is it because there is some kind of relationship, connection, direct spillover, as it's often called, of the dependent variable from one county to another? Where we might then go and say, actually, I would expect high wind damage in one place to be along with high wind damage in another place. Or, in the other example I gave from my own research, if a person is skeptical about testing, it may well be that their neighbors are skeptical about testing too. Because they talk to each other and they might convince their neighbors. A clear spillover of whether or not people are likely to get tested. That would be spatial lag regression. It could be spatial error regression, where we think there's something missing from the data set, where we might say, okay, there could be other factors like altitude that might affect, or aspect, probably aspect more than altitude really, in identifying the extent to which someone's going to have damage from straight line winds. If you're on the side of a hill that is facing the wind, you're going to get more damage than the side that is being blocked by that hill. But I didn't have that data. I didn't use that data. So there's something else going on that might produce a spatial pattern, and that would lead me to go with the spatial error regression. Likewise, in terms of the people's likelihood to get tested, there could be many other factors. There could be, say, language barriers that would prevent people from getting tested that I didn't account for. And so that's something that might suggest a spatial error regression in that context. Or it could be the, really probably not as much with the damage one, but we say, okay, geographically weighted regression, as I carried out for the COVID response example, where the factors that affect the relationship between one variable and the dependent variable may not be constant throughout the study area, especially when one of those is the approval rating of the governor. Well, when you factor in, there's New York, Ohio, Pennsylvania, West Virginia, parts of Maryland, Kentucky, Virginia, North Carolina, Tennessee, South Carolina, Georgia, Alabama, and Mississippi. If I've counted right, that's 13 different governors. So to assume that the approval rating of the governor is constant when the governors themselves are different and they have different policies, different actions. As we saw, Governor Kemp in Georgia had a very different approach than Governor Justice here in West Virginia. That would lead to picking geographically weighted regression for that particular analysis. So a lot of this is really to think about what kind of question are you trying to answer here, and to think back. Okay, there was something in the lab that was similar to this. I wanted to find whether or not tornadoes were clustered. Well, okay, then trying to identify whether or not vaccine sites are clustered would be the same thing. Different approaches to point pattern analysis. So to think about that analogy of, here is the kind of question I want to ask. Are attributes clustered? Using variables to predict. Location of point patterns. Assessing predictions. Making the predictions, assessing them. Although over here we use the R-squared on the associated p-value or the AIC value to make that comparison. Are group means equivalent, either a t-test or ANOVA? So the main thing is to think through, this is similar to what, and make that decision. And as I said at the outset, I said this is preparing you for the last lab. In that last lab, I will give you a series of questions. And I'm not going to tell you what to do, what technique. I just give you the question. And it's up to you to pick a method, justify that choice, and justify the parameter choices, like what spatial weights matrix are you going to use if you're picking spatial autocorrelation. So making those determinations, justifying them, and presenting the results in a clear, coherent way to convey as much information as you have about that initial broader topic or subject of inquiry. So that is really setting up the last lab, which is what you're going to be doing for most of the rest of the semester, is just this one lab. It's much larger than the others, and it's going to be taking pretty much the whole time. Likewise, the last quiz, I'm going to give you a series of questions, examples that fit into these different categories, and it's up to you to identify the appropriate method for each of those techniques. So that is really, that is that. That is the subject and an overview of picking the right technique. As always, I encourage you, I implore you to ask questions in class. I encourage you to ask questions through email. I'll tell you right now, this quiz 7, in basically every single year I have offered this course and had a quiz like this, it has been the lowest grade quiz. This might seem deceptively easy. You might be thinking and approaching like, oh yeah, I can do this, not a problem. This is not typically an easy quiz for people, so I encourage you to reach out if you have any questions in class by email so that you can get as prepared as possible in that quiz, as well as in preparation for doing that final lab and getting as good as possible on that. So please ask questions. And maybe yes, maybe no, in terms of whether or not I will see you at the next video. There may not be a next video. So I hope you, if not, I hope you have had an enjoyable time for this course. I'm sure I have asked you, I know I've asked you to do a lot of work for this, but I hope you have learned something. I hope you have learned quite a bit through this, both in terms of the analytical techniques, as well as writing and presentation of those results. And even though I have mainly just been looking at you through a camera lens, it's been enjoyable having people in class. And I hope you have, at least in some measure, enjoyed it too. And if you are graduating, congratulations and good luck on your future endeavors. If you're not graduating, I hope to see you in the fall in the halls of Brooks Hall. To actually see you in person again. So have a good one.